Hello everyone, I welcome you all for this session on series faults. Let us see what are the causes for series fault. The series fault may occur due to the mechanical damage in the transmission line. So due to the aging of the components, wear and tear may happen. These conditions may result into a series fault. Malfunctioning of the protecting devices may also causes the series fault. For example, the wrong functioning of the circuit breaker or the relays or other protecting devices which we have connected in the circuit for the protective purpose. In the selection breaker concept itself, I have told you that the circuit breaker will operate based upon the tripping signal received from the relay circuit. If the relay failed to identify the actual fault or the overloading condition, so there is a chance of sending a wrong signal to the circuit breaker to isolate or to open the faulty part from the section. So it may not be the actual fault that will leads to the malfunctioning of the protecting devices. So in that condition, you will isolate the circuit. So thereby it will result as a series fault condition. Another reason is maybe due to the external objects like the falling tree branches on the transmission lines may also cause the series fault. So if you observe all the above 3 points, majorly it opens the circuit. Thereby the series fault is also called as open conductor fault. Coming to the classification of the series fault, the series faults are classified based on how many number of conductors are in open condition. That is, we have one conductor open fault and two conductor open fault and all the three conductors open fault. What is the effect of series faults on the system? What will happen if the series fault occurs in the power system network? This series fault causes the system to be unbalanced. So what will happen if the system moves to the unbalanced condition? Because of the unbalanced condition of the system, unbalanced currents start flowing in the rotating machines. Because of this unbalanced current, harmonics will develop in the rotating machine and it may increase the heat of the machine, thereby it will damage the windings permanently. So we need to isolate the faulty section of the system as soon as possible to prevent the other components from the damage. Open conductor fault. So what is the circuit that we are going to use to do the analysis of the open conductor fault means? Let us consider the RYB lines, or you can say the ABC phases. So now suppose let me cause any fault, so which is going to occur with respect to these terminals may cause the one conductor open fault or two conductors open or all the three conductors may become open due to the above fault conditions. Suppose the fault has occurred with respect to the phase A. So now you can represent the phase A as like this. Suppose let us say this is fault point. And because of this A phase, the current will not be there. So what is the IA current? IA current will be 0, but IB current will be there and the IC current will be there. So what is the voltage here? The voltage of the phase A will be there, measured between these two terminals. So let us give these two terminals as A and A prime. So you will measure the voltage across A prime as the voltage with respect to the fault terminals. So this is how you will represent. Suppose if it is a two conductor open fault, here we will have a B and B prime and all the three conductors are open, means we will have here C and C prime. The voltages measured across the each phase will be represented with respect to these two terminals. Now coming to the sequence network, the series fault also fall under the category of unsymmetrical fault. Whenever we are doing the unsymmetrical fault analysis, the unbalanced vector can be represented by three sets of balanced vectors. Those are nothing but positive, negative and the zero sequence. So however, we have taken three different networks for the representation of the shunt fault. Here also we need to represent three networks, that is positive, negative and the zero sequence for the analysis of series fault. So let us see how to represent that. Let us consider this as a positive sequence network. So now the positive sequence current can be represented as IA1. And coming to the voltage, if you take the terminals of the phase A as a dash at the terminals of the fault, that can be represented as VA dash. Similarly, let us consider the negative sequence network, and the negative sequence current is considered as a IA2. We are representing all the sequence network with respect to the phase A itself. So let us consider A dash. So the negative sequence voltage can be written as VA dash of the negative sequence. Here also you can represent VA dash of the positive sequence. Now coming to the zero sequence network. So this is the zero sequence current, and so this is VA dash of the zero sequence component. So for the analysis, here I am going to assume the voltage which is measured at the point of VA dash can be represented as a voltage with respect to phase A. So every time wherever we have a VA dash, I am going to represent that is the voltage with respect to phase A, just for the sake of simplicity. So now let us start with the series fault analysis. So in that, the first one is one conductor open fault. So here I am taking the phases A, B, C, and we are assuming that phase A is a open circuit condition. So now let us take this as a phase A, and which is open circuited, and phase B, phase C. So now with respect to this terminus, the fault has occurred. Let us assume. Now the fault current, so IA is equal to 0 and IB current will be there, IC current will be there. Then what is the voltage across this? VA dash will be present, but VB dash and VCC dash voltages will be 0. So therefore, the terminal conditions can be taken as IA is equal to 0 and VB is equal to 0, VC equal to 0. So therefore, the symmetrical components can be determined by using these line currents and the phase voltages. Let us start. And similarly, however, we have done for the shunt fault analysis, similarly for the series fault also, depending upon the how many terminal conditions we know, preferably we will be doing the symmetrical component calculation with respect to those terminals. Here we have two values for the voltage, so we are going to find out the symmetrical component with respect to the voltage itself. VA naught is equal to 1 by 3 into VA plus VB plus VC, and we know VB and VC are equal to 0, that is equal to 1 by 3 VA. So similarly, VA naught can be written as 1 by 3 times of VA, A into VB plus A square into VC, that is equal to 1 by 3 VA. So VA2 is equal to 1 by 3 VA plus A square into VB plus A into VC. So this can be, again here VB, all the equations VB and VC both are equal to 0. So finally you will get only VA by 3. So therefore from these three equations we have a condition that VA naught is equal to VA1, that is equal to VA2. So this is one condition that we need to represent the interconnection of the sequence network. And let us see what about the current equations. We know current IA is equal to 0. So this can be written as IA naught plus IA1 plus IA2 is equal to 0. So from these two conditions, we can say that the sum of the currents at a particular node is equal to 0, and similarly the voltages of the each branch, that is VA naught is equal to VA1 and VA2. So therefore, from these two equations, we can conclude that the system or all the sequence networks are connected in parallel combination. So here we don't have any through fault impedance. So directly you can connect all the networks in parallel connection. Now let us see the interconnection of the sequence network. So let us consider positive sequence network, negative sequence network and the zero sequence network. So now let us represent the currents here. The positive sequence current is IA1 and this is IA2 current, and the negative sequence current is IA0. So here also you can represent the same IA1, IA2 and IA0, and you can represent the voltages. So that is the voltage VA1 and this is the voltage VA2 and this you can say the voltage VA0. Parallel connection is the all the starting ends will be connected, or let me say this is A and A dash, A and A dash, here also A dash. Parallel connection means all the A terminals will be connected together and all the A prime terminals will be connected together. So this is how you can make the interconnection of the sequence network for the analysis of series fault, one conductor open fault. Now coming to the two conductor open fault. So here it is the condition where the two conductors are in open condition. So now we are considering phase B and phase C are open circuited. So now let us consider phase B and phase C are open circuited. Now you can write the terminal conditions here. So here the current IA will be there and VA dash is equal to 0 because it is short circuit condition. Here with respect to this fault terminals F dash, this is short circuit, so VA will be equal to 0, then IB will be equal to 0, IC will be equal to 0 because here we don't have any path for the current to flow. So therefore the terminal conditions can be written as IB is equal to 0, IC is equal to 0 and similarly the voltage with respect to phase A is equal to 0. So by using these things we are going to find out the symmetrical components. So which one we will take preferably means here we have two conditions for the current equation. Symmetrical component relations. IA naught is equal to 1 by 3 times of IA plus IB plus IC. So here IB and IC values are 0. So we will have IA by 3 and IA1 is equal to 1 by 3 times of IA plus A into IB plus A square into IC. So that is equal to again here IB and IC. So these are the two terminal conditions that we have taken. So therefore this also will result into IA by 3 and IA2 is equal to 1 by 3 times of IA plus A square into IB plus A into IC, that is equal to IA by 3. So from these three conditions we got one relation that IA naught is equal to IA1, that is equal to IA2. So by looking at the equation itself we can come to the conclusion that all the sequence networks are connected in series connection, then only all the currents will be equal to each other. Now let us see the voltage condition also. So we have VA is equal to 0. So VA is equal to 0 means the summation of all the sequence components will be equal to 0. VA naught plus VA1 plus and VA2 is equal to 0. So this condition also resembles the series connection of the circuit. Algebraic sum of the voltages around any closed circuit is equal to 0. So based on these two equations we can interconnect the networks. Now let us see the interconnection of the sequence network. Positive sequence network, negative sequence network and the zero sequence network. Now let us consider with respect to the fault terminals F dash. In the series connection, the finishing end of the one network will be connected to the starting end of the other network. So let us do that. The finishing end of positive sequence network is connected to the starting end of negative sequence and finishing end of negative sequence is connected to the starting end of zero sequence. Similarly, F dash is connected back to the F. Now let us mark the currents here. Let me give this as a IA1 and now you can say and this as a IA2 value and this as IA naught. So the same can be represented. So all these currents will be equal, and this loop forms one complete series connection. So now this is how we can represent the sequence network to do the analysis of series type of fault. Coming to the 3-conductor open fault, this is the example for the external object falling on the transmission lines due to the cyclone effect and all. If any tree branches fall on the transmission line, all the 3 lines will get disconnected from the supply. So it will become all the open conductor fault. So this is the condition where we cannot consider this as a fault condition only, because it is completely, the load will be completely isolated from the supply system. Actually, we no need to do any analysis for these kind of faults. So IA is equal to 0 and IB equal to 0, IC equal to 0. So here all the phase currents IA, IB and IC are equal to 0. So even if you find out the sequence component of the currents, so these values also will result into 0. So whatever it is, you will take 1/3 times of IA plus IB plus IC. So all these values, if you substitute these values in this formula, so all these values also will result into 0, because all these 3 values are 0. So whenever the currents are equal to 0 in the sequence networks, then we no need to go for any analysis. So I hope it is clear. Thank you.